number 6. Methanoic acid. So methanoic acid HCOOH is weak acid when methanoic acid is dissolved in water and equilibrium is established. This equilibrium involves H plus ions and methanoate ions. So question A, methanoic acid is an example of Brønsted-Lowry acid. The methanoate ion is an example of Lewis base. Explain these two states by reference to the equation above. So methanoic acid HCOOH is Brønsted-Lowry acid, Bl acid, because HCOOH is Brønsted-Lowry acid because it donates H plus, and methanoate is Lewis base, Lb Lewis base, because it donates electron pair. So if you write just electrons, incorrect, electron pair or pair of electrons. Next, what's the pK? Methanoic acid. So pK is K is given acid dissociation constant. So pK, just use formula minus log K. Here you get 3.749. So you must have 3 significant figures, so 375. Here 375. Next question, buffer solution. If 100 cm3 of 0.1 mole per decimeter cube methanoic acid solution is mixed with 300 cm3 of 0.1 molar per decimeter cube, so the methanoate solution 400 cm3 of buffer solution is formed. Explain what's meant by the buffer solution using at least 2 equations to show how it works as a buffer. So buffer solution definition. So we must write definition. Buffer solution is the mixture of weak acid and its conjugate base salt. Conjugate base salt. So here we have methanoic acid and conjugate base salt is sodium methanoate, which is resistant to pH change, when small amount of strong acid or base is added. So please remember, buffer solution is a mixture of weak acid and its conjugate base salt, which is resistant to pH change, so there will be very small pH change. So when small amount of strong acid or base is added, so we need to use 2 equations to show that it works as a buffer. So methanoic acid, so here HCOOH, can react with added strong base, small amount of strong base, OH minus. So in this case you get methanoate and water. Next, when you add strong acid, so acid then is H plus, so H plus will react with methanoate, so you get methanoic acid. 2 reactions shows that this is buffer solution. Next, so here 0.730 grams of HCl gas is dissolved in the 400 cm3 of buffer solution. Calculate the pH of solution found when all of the HCl gases react with the buffer. In this case we are adding acid, so you were adding acid, so we're gonna use this reaction. Okay, so acid will react with methanoate, so methanoate HCO minus plus H plus equals to methanoic acid. So in the buffer solutions we use ice table, so ice, why it's called ice, because I is initial, C change, E equilibrium. So initially initially here methanoate we have 0.1 300 centimeter cube. So how we gonna solve? So 300 divided by 1000 to get decimeters, multiply by 0.1, we get 0.03. So here we have 0.03. Next, for the methanoic acid, which is 100 centimeter cube and 0.1, again 100 divided by 1000 and multiply by 0.1, you get 0.01. So if you ask why we divide by 100, divide by 1000 and multiply by concentration, it's just simple formula for concentration. Some number of moles equals to concentration multiplied by volume. Volume must be in decimeter cube. So initially we have 0.01 methanoic acid and we get 0.730 grams. So we can calculate the number of moles of HCl added. So divide by 36.5, we get 0.02 moles. So here we have 0.02. As you can see here, limiting reaction is acid, so all acid will be reacted, so there won't be any acid in the equilibrium. So as we have 0.02 of acid reacting, so methanoate also as well will be 0.02 more subtract, we get in equilibrium 0.01 moles of methanoic acid. And here we are forming methanoic acid, so plus 0.02, you get 0.03 moles. So the volume is 400. So in this case, so you already formed buffer solution. So in this case, you can directly use number of moles in your Henderson-Hasselbalch equation, which is pH equals to pKa plus log of conjugate base divided by acid's concentration. So pKa we calculate 3.75 plus log, here we have 0.01 and here we have 0.03. So 0.01 divided by 0.03. So 375. Here you get minus 0.48 and at the end you get 3.27. Okay. Henderson-Hasselbalch. So this here we must actually use concentration, but the volume is fixed. So if you divide by 0.01 to 0.4 and 0.03 by 0.4, 0.4 will be cancelled anyway. So we can directly use number of moles. And the last question, titration here. Methanoic acid can be oxidized by acidified potassium manganate solution. 50 centimeter cube solution methanoic acid needs 70.25 centimeter cube unacidified 0.02 moles of decimeter cube per decimeter cube solution of permanganate for complete oxidation. Calculate the concentration of the methanoic acid solution. So here we can easily find out the number of moles of methanoate which is reacted. Again, concentration multiplied by volume. Volume must be in decimeter cube. So we have concentration which is 0.02 multiply 1725 divided by 1000. So let me calculate 1725 divided by 1000 multiplied by 0.02. We get 3.45 10 to the power of minus 4 moles. Okay, from the equation you can see that 5 moles of methanoic acid reacts with 2 moles of methanoate. So 5 moles of methanoic acid reacts with 2 moles of MnO2 permanganate, and we have here 3.45 10 to the power of 4 moles of permanganate. So 3.45 10 to the power of minus 4. So here we can put x we can easily calculate. So we just multiply by 5, divide by 2. You get 8.625 10 to the power of minus 4 moles. Okay, so here you have volume, so we need to use the formula. So concentration equals to the number of moles divided by volume. So 8.625 10 to the power of minus 4 divided by 50, which is divided by 1000. Okay, we divide by, so this number we divide by 0.05, so you get 1.725 10 to the power of minus 2 mole per decimeter cube. Okay, so this is titration, so number of moles. So we just you just need to calculate number of moles and convert to the other substance, yeah, and then using again the same formula we get concentration. Okay, this is last question for the question 6.